Okay, so welcome to the course Deep Learning, Theory, and Data Science. I wanted to start today's lecture by just clarifying what is the definition of a margin, because it appears in the homework, it appears in the lectures, and maybe this is one of those things that I hope you would remember after the course. So maybe we should make sure that the definition is clear. So in the homework, the definition of a margin is it's equal to FICC minus FICC prime, where FIC is a vector in RC. Capital C is the number of classes, and FIC are logits. So these are the logits of the ith example in the cth class. And basically you can write these logits as FIC as the inner product of HIC, which is a feature, with WC minus WC prime, which are classifiers, plus BC minus BC prime, which are biases, right? And so this should explain what is the relation between the logits and the features, the classifiers and the biases, and also the relation between the margin and the logits, right? So these are, oh, here it should be CC prime, sorry, FICC prime, right? And this is a logit. Does this make sense? Does anyone have any question about this definition? I want to make sure everyone understands this because this is something quite important.
Professor, could you explain why would the classifier be the difference of 2WC again?
So the what I mean here is that this is two classifiers. So it's the classifier of the, oh, this is, yeah, sorry. Let me fix the equation 1 second. So this is, let me copy this here, like this, and like this, okay? So the answer to Neo's question is that WC is a classifier of class C and WC prime is a classifier of class C prime. Does this answer your question, Neo?
I see, that makes more sense now.
Okay. And basically it's just the difference between the logit of class C prime and the logic of class C.
One more question.
Mm-hmm.
So FICC, the first I, it's clear what the I index is referring to in the equation. Then the CC I wasn't too sure what does the CC correspond to. Would you be able to?
So FICC is HIC inner product WC plus BC. So it's basically the prediction of the cth class for an example that actually belongs to the class C. So the first C is the true class, right? Because it's this thing. The second C is an index in logits. So in general, you would have FICC prime where this would be C prime and this would be C prime. Does this make sense?
Yeah, thank you very much.
Okay. By the way, in future lectures, not today, but in future lectures, I'm going to give this thing a name. So this is going to be the class or the true class, and the index in the logits I'm going to call a cross class. So just one day this will appear again. Not today, not tomorrow, but one day. So does anyone else have any questions? Any questions about the margins?
Oh, and the I is the index of the example, right? You have n example.
Yeah.
Okay,
First
thank you.
cat, second cat, third cat, fourth cat. And notice that in one of the lectures, we had a theoretical derivation that proved that a certain classifier converged to a max margin classifier. Do you remember such a thing in the non-distant past? In that case, there was no bias. So the margin in that case was simply equal to something like HIC inner product WC minus WC prime. And the reason there was no bias is because you cannot prove that claim if you have a bias. Or I'm not aware of anyone who proved that claim if there's a bias. So unless there's other questions, I'm going to proceed to today's topic. One last chance to ask a question about the margins. No questions. Okay. How do you say you may object now or forever hold your silence? There's such a thing in Christian weddings, right? Is it the thing in Canada? It's not Christian weddings? In Jewish weddings, there's no such thing. The rabbi doesn't stop for anyone. Is it defined without absolute value? Yes, it is defined without absolute value. Speak now or forever hold your peace. Yeah, that's what I meant.
So to get the original class, do we have to look back in what we inputted? Like we have inputs, comma, labels, sorry, images, comma, labels. Would that be the original label?
Yes, yes, the true class. Yes, the original label. Yes, yes. Justin asks, can't you define W equal to WB and XI equal to X1? You can do that, Justin, but the theorem still doesn't give what you want it to give. You can look at the paper that I mentioned in that lecture. They have a subsection on biases, and you would see how what you wrote is not enough. But I don't want to go into these details because it's too nitty gritty. Okay, so we move to today's topic. So today we're going to talk about something called the unconstrained features model for the MSE loss and how it leads to neural collapse. So specifically, so this is again a reminder of what neural collapse is. So neural collapse is a collection of 4 properties that emerge in the last layer of deep networks. And the properties are within class variability collapse. The class means converge to very special geometric structure, which is called the simplex ETF. There is self-duality, which means that the classifier and the features converge to each other, and the decision of the classifier converges to the nearest class center. So I think I've mentioned this many times at this point, so I'll just skip to the point. So today we're going to discuss a paper which is called Neural Collapse with Unconstrained Features. This is by Mixon, Parshall, and Pai. I believe you actually pronounce this P, but I like Pi better for some reason. So they say neural collapse is an emergent phenomenon in deep learning that was recently discovered. We propose a simple unconstrained features model in which neural collapse also emerges empirically. So notice that the emphasis here is on the word model. By studying this model, we provide some explanation for the emergence of neural collapse in terms of the landscape of empirical risk. Okay. So their goal is to propose a model and to prove that under this model, neural collapse occurs. Could you repeat what the constraint was on the features in previous work? When you say previous work, what do you mean, Jack? The neural collapse work? Previous to this paper. You mean, for example, in this slide, what is the constraint on the features? When you say what is the constraint on the features, do you mean to which geometry do the features converge to, or do you mean, I'm not sure what do you mean?
It might just be a semantic thing, but the new paper says unconstrained features.
Yes.
Right. So I was wondering what the constraint was before.
Oh, I'll explain that in a minute. Yeah.
Okay.
So what is the unconstrained features model? So first of all, they consider the mean squared error loss, which is different than cross entropy loss. And the mean squared error loss, we've already seen it in this course. So the mean squared error loss is W, which is the classifier, multiplied by the features, plus a bias minus one hot vectors, which we're denoting here by EC. And you can write this as a summation over all the different features. And notice, oh, there should be a summation over C here as well. Sorry for this mistake. Sum over C from 1 to capital C. This is the ugliest sum I've ever seen in my life. Let me try to beautify it a bit. There is no way. Okay. It should remain horribly looking. So notice that you can think of this as a function of three variables: the classifier, the bias, and the features. Now, Jack asked, why is this called the unconstrained features model? And why was the previous model, or yeah, why is it called the unconstrained features model? In what way is it unconstrained? Does anyone have any suggestion? Can anyone answer Jack's question, basically?
You're optimizing over the H as well. Like they're not constrained to be the output of a neural network.
Yeah, exactly what Tristan said. So Tristan is saying that in a deep network, you would have HIC be a function of the input images with a bunch of parameters theta, right? So there would be a very deep network that would do feature extraction, and your HIC would be constrained to be the output of such a deep network. Now, in this work, they say, let's just assume that the HIC are some vectors in, some high dimensional space, and they're free to move as they please. Does this distinction or this difference, does it make sense? So you're assuming that the features are just free to roam high dimensional space as they please, and they're not constrained to be the output of a network. Now, you can...
Sorry, I have
Yeah?
a question. You mean they're not a function of images and theta anymore, right?
That is correct.
And they are independent of the images, statistically. No, not statistically. They're just not the functions. Maybe they're dependent.
They're just some vectors which are not a function, which are not a nonlinear function of some things, right? And you can write these MSE laws in a fancier way as W multiplied by H. H is a matrix of features minus an identity Kronecker 1 transpose. So W here is a matrix which contains in its rows the different classifiers WC. H is a matrix which contains in its columns, HIC, where I goes from 1 to capital N, and C goes from 1 to capital C. And specifically, the matrix H is of size P times NC. P is the dimension of the features, and NC is the number of examples in the data set, right? We have N examples per class and C classes. And the bias is just a vector in RC. Now, why are we doing here an identity Kronecker product with a once vector transpose? So an identity is a matrix that looks like this. Let's say we have 4 classes. And imagine you assume that there is 5 examples per class. Then this is equivalent to doing the following thing. You take this matrix and you just copy it 5 times, right? So you create this bigger matrix which just contains copies of an identity. Okay, now the notation NC could make ambiguity as it's also abbreviated. I know, yeah, that is. I thought it would be cool to have NC both here and there, but you seem to interpret cool as ambiguity. Yes, okay. I agree with what you say. Now, how would we know if we obtained neural collapse in this model? How would we know? So they say that neural collapse is equivalent to these 3 properties. The first property says that WW transpose is equal to a scalar times an identity minus 1/C11 transpose. Can anyone tell me what does this mean? Oh, please ignore these things. This is a mistake. Ignore this. Yes. Yes, so Jack says that this means a simplex CTF. So any matrix that satisfies the property that A transpose A is equal to some scalar times identity minus 1 transpose over C is a matrix that is in fact a simplex CTF, right? So the first equation says that W is a simplex CTF. So this is what we originally called NC2. What does the second equation tell us? The second equation tells us that H is 1/square root of n multiplied by W Kronecker with a once vector. What does this mean? I would prefer actually to write it as 1/square root of n W transpose Kronecker 1 n transpose. This looks more appealing to my eye. What does this property say to you, if anything? So Etienne says the features converge to the classifier. That is, in fact, correct. That is correct. You see, on the left, you have features. On the right, you have classifiers. But is this the only thing that this equation tells us? Does this equation tell you anything else? So the features converge to the classifier is equivalent to NC3. So let me just write here NC3. But what other property is hiding in this second equation? I noticed, by the way, I was watching the YouTube video to make sure the quality is high. And I noticed that whenever I write on my tablet, you can hear like it's like a bird knocking on wood, right? Does anyone know how to fix this? Because I bet this is so annoying. Maybe I can take this away from the, I think it's because my microphone is extremely sensitive. But I don't know how to.
Are you using the built-in mic for the iPad?
No, I have the highest state-of-the-art equipment. You see?
Oh wow!
Yeah, I spent a lot of money.
I don't know then. You need a less good microphone.
Yeah, that's exactly the lesson in life. Because this microphone doesn't work on Skype properly, doesn't work on Zoom, doesn't work for recording. It's just too sensitive. If anyone knows how to fix this, I would appreciate ideas. You can email me and I'll be sure to implement that. Yeah, so what else does this equation say to you? It says H equal to W transpose Kronecker once, right?
Is this the collapse of interclass variability?
Yeah, exactly, Tristan. So notice how W transpose Kronecker once is basically copying the classifier many times, right? And so it's saying that the features, so let's write it's H, let's say 1, 1, H, 1, 2, H, 1, 3, where the first index, okay, it's HIC in general. So let's do H 2, 1 and 3, 1. Okay, so these are the examples in class, 3 examples in class 1. Then you have, let's say, 3 examples in class 2. So it would be H21, H22. Oh, I keep getting the indices incorrectly. My bad. It would be H1, 2, 2, 2, H 3, 2, etc. Right? So you can see there's a bunch of different features here. And on the right-hand side, you would have W1, 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 W2, 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 because of the Kronecker product. Does this make sense? So the Kronecker product with the once vector is just copying the classifier many times. And the equation is saying that the features are equal to the classifiers Kronecker with once, which means copied classifiers. So this equation also tells us NC1 holds because the within class variability would be 0. Any questions or no questions? No questions. The third equation tells us that the bias is simply equal to a once vector over C. So it just specifies explicitly what the bias vector is going to be. Now, notice that here you can see a very explicit scaling between the class means and the classifiers, right? If you look at the original properties, the properties said that there is self-duality. So the vectors are equal to each other up to some scalar, but I didn't specify what the scalar is, right? In their work, they specify the scalar and they say the scalar is equal to 1 over square root of n. And they also specify explicitly the bias, which is something that the original work did not do. Do they normalize H somehow by dividing by square root of n? No. So at this point, you can think of this as almost like a definition of neural collapse, right? In terms of their notations. What is the role of square root of n? So the square root of n, okay, let me explain it from a different perspective. Here you have an objective, right? It's a MSE loss. Imagine you optimize this MSE loss and you converge to neural collapse, right? Then it would mean that there is self-duality and that there is some relation between the class means and the classifiers. Now, imagine if someone whispered in your ear that, in fact, self-duality holds up to a scalar, which is square root of n. So it's just telling you some extra information about neural collapse. Not only is there self-duality, but the ratio between the vectors is square root of n. Does this make sense? At this point, it's unclear why it's square root of n, but their proof shows why it's square root of n. Okay, so here's again the MSE loss written in this fancier manner. And one could consider to do gradient flow on this MSE loss. Gradient flow is just gradient descent as you take the limit of step size to 0. Okay. Now, here you can see the equations of gradient flow. So how do we obtain these equations? Just by deriving this quantity with respect to the W, the H, and the B. So for example, if I derive with respect to h, I would get, so dl to dh is equal to W transpose WH plus B1 transpose minus I Kronecker 1 transpose. Why is this the derivative? Does anyone know? Do people know how to derive this type of quantities in general? Mixed emotions? No, not quite. So if someone wants to become an expert on derivatives, I would suggest memorize the matrix cookbook. I cannot stress enough how useful it is to memorize the matrix cookbook. What happens to the norm? There is no norm. So if you derive, so okay, notice that L is a scalar, right? It's a scalar, which is dimension loss. H is a matrix. So if you derive a scalar with respect to a matrix, you expect to get a matrix, right? And so this is the matrix you get. So there is no norm. I'm not sure what you mean by what happens.
I mean, so when we derive the derivative, we just ignore the norm and take the derivative of the things that's inside.
Yes, but there's also the, how do you call the inner derivative? Does this word make sense? Inner derivative? It does. So there is an inner derivative here with respect to h, because the inner derivative is W transpose, which creates this thing.
Yeah. Okay.
If someone wants to, okay, if you don't like the matrix cookbook, then one way you could derive this by yourself is just do dl to dhij. So this is just scalar derivatives that you definitely know how to do. And then just construct a matrix where each entry is dl to dhij, and you would just get the formula I wrote. Would just be very, very, very tedious. Problem set 1. Oh, okay, so you've already done, okay, yeah. Oh, I see, so you did this in problem set 1. It's missing as, okay, you're correct. So let me put a half here, interesting. Thank you for the correction. I see. Okay, so it's good that you did this in problem set 1. You're gradient experts. Now, why do I have here a minus? Because we don't want to go in the direction of the gradient. We want to go in the direction of the minus gradient because we want to minimize the loss. And then you do the same thing for W and the same thing for B. Okay, I want to do those. You can just do it yourself. Now, in all of these equations, this is like gradient descent, but in continuous form. That is correct in yours. Now, in all of these equations here, in this system of differential equations, I introduced this notation Z. Z is basically what's written here in the parentheses, and I call it a residual. Why? Because it is a residual, because Z is basically WH plus B, which is the prediction, minus the target. So it's just a residual, right? A prediction error. Now, notice that this is a nonlinear differential equation. Why is it a nonlinear differential equation? Does anyone know? Are there differential equation experts in the crowd? I bet there are.
Because you have products of the variables.
Yeah, exactly. So you have here W multiplying by H, and this thing is going to multiply it by W or by H again. So it's a very nonlinear differential equation, right? And so what the authors of this paper propose, if you had to propose something, what would you propose? How would you proceed? Would you solve a nonlinear differential equation? That's crazy, right? Too much work. So what would you do? Approximate, estimate with Taylor. Estimate with Taylor is a good idea. iterative algorithm, linearize, simulate. Simulate is not enough. Linearize. So what they did was actually an approximation. And what they suggested was the following. What happens if we look at the dynamics when it is initialized close to the origin? So close to the origin means that W and H are very small, right, in norm. If W and H are very small in norm, then this term becomes negligible, right? So because W and H are very small, W times H is also very small. And therefore you can just ignore this part and you get a simplified set of equations because you just get W multiplied by this thing, which is much more pleasant. And so this is what happens here. So you get this simplified set of equations where instead of Z, and Z, you have R in all of these places, and R is just missing this annoying part of W multiplied by H. It is again not linear, says Amreza. Yes, but it turns out that it is very solvable. It is very solvable. In fact, it is. Okay, we'll discuss it. In fact, it's very. I think it's even linear. It might not look linear, but it's even linear. You're saying it's not linear because B and W interact with each other, right?
Yeah, exactly.
Yeah, but we'll see that this is not a problem. Not a problem. Now, I want to emphasize that this is a very strong assumption to be making, right? That you are initializing next to the origin. It's quite strong of an assumption, I would say. Could you explain how this approximation works again? Yeah, you just say, I don't like this term, forget about it. That's it. This is how it works. Answer the question. So the reason you say forget about it is because you assume that I assume there's no need for formality. So you assume that W has an L2 norm which is small, and you assume that H has an L2 norm that is small, so W times H has an L2 norm that is small, whatever norm you prefer, right? And as a result, W times H is negligible. Does this answer the question you? Okay. Did they realize the WH term is small in experience you can show? No. They did not. Not as far as I'm aware. Yes, so this is where experiments deviate from theory, it seems. But it's okay. So, okay. So now we have this simplified dynamics. And one can prove, and they prove, the following theorem. So let us parse what does this theorem say. So this theorem says, assume that you initialize your bias to be a zero vector. That's actually a very reasonable initialization. And in practice, if I remember correctly, this is actually how people initialize biases, if I remember correctly. Then the solution to the simplified differential equation in the previous slide satisfies the following properties. So let's start with the second property because it's easy. The second property says that the bias as function of t is equal to this very simple equation. So why is this a simple equation? Because this is a once vector multiplied by a scalar, and the scalar is just some simple function of t. Now, the first bullet is a bit more hard to digest. So what does it say? It says, imagine you have the tuple of the features and the classifiers at time t. Imagine that you scale it by some quantity, right? So it's like a scalar. Let me highlight here what's important. Oops. Let me highlight. So you have the features and the classifiers are close to the features and the classifiers at initialization projected onto some linear subspace. And the proximity is decaying exponentially with time. In simple words, what does this say? What does this mean? In simple words, what does this mean? If it means anything to you. They converge to the origin? No. So the features and the classifiers at iteration t, I'll explain in a second what t is. That will be explained. So the features and the classifiers at iteration t are close to the features and classifiers at the 0th iteration once projected to the linear subspace. Not quite, Gina. What does this mean? So the features and the classifiers are converging to the linear subspace. That's what this means. They're converging to the linear subspace, and more specifically, they're converging to the features and the classifiers at initialization after they're projected onto the linear subspace. Does this make sense? What is E? I will explain this as well. These are all good questions that will be explained.
I have a question.
Mm-hmm.
But the first term is multiplied by e to the minus square root nt.
Yes.
So those h of t and w of t are blowing up to infinity, but then it's tempered by the decay of that exponential. And that's what converges to the projection.
So, yeah. So you're saying that the w and h are blowing up to infinity, but that blowing up is tempered by the exponential to the negative. And what was the rest of the sentence?
And then so that product is what converges to the projection.
Yes. There's
So
actually there's actually some subtleties about the work which I think you might be pointing to, which I would prefer not to discuss at this point because it would confuse everyone. But I'd be happy, more than happy, to discuss this at the end of the lecture.
Okay.
But I think what you're, I can sense where you're going with this. I think you are touching on an important thing, let's say. So, but it does make sense, the general idea, right? So the features and the classifiers are converging to the H0 and W0, which are the features and classifiers at initialization, after you project them onto a subspace. Is it more about the direction converging? Maybe I can make a picture, by the way. Maybe I can draw a picture. So here is a linear subspace of some sort, right? And you initialize your optimization. And the idea is that you find yourself very fast on this subspace. So this is the subspace T. This is H0, W0 at initialization, right? This is the projection. Maybe I should do it like this. Projection onto the linear subspace, right? And they're claiming that you get rapidly towards this projection. So your trajectory might be something like this, right? Does this drawing please anyone? Does this make sense? It does, okay. So let's answer Neil's questions. Neil had many questions. So the first question Neil asked was, what is this linear subspace? So the linear subspace is defined over a tuple of H and W. And the subspace is the set of H and W's that satisfy these constraints. So in simple words, what are these constraints? So this constraint we've already seen, right? This constraint says that there is no within class variability and that there is self-duality. So let's write that down. No within class variability and also self-duality, right? Do you recognize this equation that we've seen only a few minutes ago? Do you recognize it? You do? And the second equation here just says that the classifiers have zero mean. So if you just average all the classifiers, you would get zero. So sum over WC, 0. So hopefully we've answered Neil's first question. Neil, are you okay with the answer? Satisfied?
Yeah.
Okay. Now, Neil's second question was, what is this E norm? So the E norm is just the usual, it's just the Frobenius norm of the features plus the Frobenius norm of the classifiers, right? A very natural norm to define. Now, associated with this norm is the inner product space, which would be, you know, inner product of H, W, tuple, H, wiggle, W wiggle, tuple, and then it would be an E inner product, is the inner product of H, H wiggle, W, this is a Frobenius inner product. So Frobenius inner product is just the inner product that's summing and multiplying, I guess multiplying and summing all the entries of the two matrices. Have you seen inner products? Maybe I should ask, have you seen inner products? You have, right? Do you like inner products more? No, no one likes them. Okay, no strong emotions towards inner products. So again, I want to love inner products. Well, I wouldn't say I love inner products, but anyway, so what this says, again, just to emphasize, is it says that your optimization algorithm is going to converge to a point which is the projection of your initialization onto the subspace. And so this is the initialization, this is the subspace, this is the projection onto the subspace, and you're converging to this projection rapidly. Okay. Now, why would we want to converge to this subspace? Does anyone have any intuition? Why would you want to converge them? Yes, exactly, because this subspace satisfies some neural collapse properties. Does it satisfy all the properties? It does not. Which property does it not satisfy? It does not satisfy the property of ETFness, as Neil says. That is correct. So in the proof of this theorem, we must use properties, or it's easier to prove this theorem using properties of Kronecker products. So here again, here's a short reminder of Kronecker products. So aren't you all professionals, Kronecker professionals, because of the homework? I think there were some Kronecker products in the problem set. Or did you write the answer not in terms of Kronecker products? I guess you could bypass mixed product property. Yeah, again, I did not write the single most important property. Oh, I did write, it's just cut. So let me write it by hand. So it's A Kronecker B multiplied by C Kronecker D is equal to AC Kronecker E D. Okay, so here's how the proof goes. The first step of the proof is to show that the bias has a very simple closed form solution. So recall that the bias B satisfies the simplified dynamic equation B prime equal to R multiplied by ones. Ones here is a very long ones vector. Now, at this point, we can just plug the definition of R, right? We can plug the definition of R, and then we get this thing here, right? And then using Kronecker products, this simplifies to this. So does anyone see how to go from here to here? How do we get there? So there's two things. One of them is easy, one of them is hard. So the easier thing is if you have a B1 trans, no, Wolfram would not help you with this. Or I don't know how you would use Wolfram for this actually. Maybe it will help you actually. Wolfram is getting smart by the day. So B multiplied by 1 transpose multiplied by 1. So notice this is just a ones vector inner product with a ones vector. So it would just give you n times c, right? So B times nc, this is what you have here, B and c, right? So this term is easy. What about the other term? So what do we get if we do identity of size c times c, Kronecker product with a ones vector transpose multiplied by ones and c? So the first step we could do is we can write the ones and c. Does anyone have any suggestion what to do with the ones and c?
Can we write it as a Kronecker of 1 with itself?
Yeah, exactly. So you just do a Kronecker of 1 of length c with 1 of length n, and then this just gives you a 1 of length nc, right? And then you use the mixed product property that we almost missed in the previous slide. And then you get identity of size c multiplied by ones of size c, Kronecker product with 1n transpose 1n. Now this is identity multiplied by ones vector is just a ones vector of length c, and a 1n transpose 1n is just n, right? So you just get a ones vector of length c multiplied by n, which is in fact what you have here. So I'm just verifying that we know how to do basic manipulations with Kronecker products. It seems like we know. Now notice at this point that we've obtained B prime is equal to a vector minus B multiplied by scalar. So what is your urge? What should you do at this point? Do you have an urge to do something? An exponential is correct, but before we do an exponential, so notice that if you have a vector prime equal to something minus a vector, it means, and the vector is not being multiplied by anything, it means that all the coordinates are just separable, right? So you have just a set of separable one-dimensional simple differential equations that you can solve. And you can, so if I denote an entry from the B vector by beta, I get beta prime is equal to n times 1. So previously it was a vector, now it's a scalar, minus c times beta t instead of bt. And Neo immediately, oh, I think Neo used Wolfram alpha to find, yeah, did he use Wolfram alpha? No, Neo immediately saw an exponential, doesn't even need to go to Wolfram, it's too easy, right? So this is an exponential because if you have beta prime equal to beta multiplied by a bunch of stuff, immediately one sees an exponential solution, right? The derivative of an exponential is the exponential. And so by noticing that the solution is an exponential and maybe thinking a little bit more, you get that this is the solution to this simple differential equation. Now, to get this solution, we also use the initial condition that was mentioned in the theorem, that the bias is initialized to 0. Does everyone know how to solve this type of differential equations? You do? Differential equation experts are sitting in this crowd. Okay, so basically we conclude that this is the solution to the bias as function of t, and unfortunately we've ran out of time. So thank you for joining and see you next time. What is Paul's online notes? Is this like a differential equation
Yeah,
textbook
it's
or
just a
something?
series of really badass online notes that basically teach you how to do all kinds of calculations.
You mean like in the
It's
context
like
of differential
it's like
equations?
matrix. Yeah, it's like matrix cookbook for ODEs.
Okay, so I have something I should memorize. Thank you for the suggestion.
So can I ask more about that thing now?
Yes, yes.